Okay, degree 2 curves. Okay, let's do cylinders. And quadratic surfaces. Quadratic surfaces. Surfaces. Okay. Now, the invention of analytic geometry is actually a breakthrough in mathematics. So the two mathematicians, Descartes, the mathematician, which is also a philosopher, the famous "I think, therefore I am." Okay, and his contemporary mathematician Feynman, a judge. Okay, a judge, and they produced. They had the same idea of of analytic geometry around the same time. The idea of analytic geometry is we use algebra to study geometry. Okay, we use algebra to study geometry. Okay, so we use algebraic equations. Use the idea. The idea is use algebra. Use algebra. For instance, equations, coordinate of a point. Okay, equations to study geometric objects. To study geometric object. Okay, geometric object. For instance, lines, planes. Okay, if we can write down the line equation, we can write down the plane equation. And to find the intersection, we need to find intersection of simultaneous solution to both equations. Okay, intersection of two lines. We just solve the corresponding equations. Find the simultaneous solution to the equation systems, and then we find the intersection. Okay. Now we also know how to do a parallel relation, and we also know how to do perpendicular relation. Okay, so we can use vectors to do, for instance, distance. Okay, distance and angles. Okay, so we can use vectors to talk about the properties of distance. Okay, distance, Euclidean distance, and angles between two directions. Angles, whether they are parallel or whether they are perpendicular. Okay. Okay. Now, so this analytic geometry, we use algebra to study geometry. A famous saying of one of the greatest mathematicians in the 20th century, Sir Atiyah. Okay, Sir Atiyah. Sir Atiyah says this: if you ask a mathematician, what do you want to study? Do you study algebra or do you study geometry? And then this is a silly question. Because Atiyah saying to ask this question is the same thing to ask people, do you want to be blind or deaf? Okay, so we cannot. So mathematics. Okay, different branches of mathematics actually is deeply interrelated. Okay, there are very subtly between different branches of mathematics. Okay, very often they are related in one way or another. So this is actually why mathematics is so beautiful. Sometimes you can, from a higher point of view, different kind of problems will turn out to be same mathematically. Okay, the abstract structure will be the same. For instance, when we talk about, for instance, slope of a tangent line. Okay, slope of a tangent line. Remember, for example, slope of a tangent line and a velocity problem. So actually, what do we do? Actually, we take a limit. Okay, slope of tangent line, we need find slope of secant line, and then take limit. Okay, take limit. So we get actually derivative of function. So this introduce derivative. Then we also have instantaneous velocity. Instantaneous velocity. Now this, although they looks different, okay, different thing, but mathematically they are the same. I.e., where actually these two thing related is actually is motivate the definition of derivative. Okay, so they are actually mathematically the same. Derivative. This gives derivative definition of derivative. Use taking limit of certain thing. Definition of a derivative. Definition of derivative. So let's see. Let's use fx minus fa x minus a. Okay, limit x up to a. So this is actually nothing else. That's derivative. Slope of tangent line is given by derivative of function, and instantaneous velocity is given by derivative of the position function. So mathematically, that's the same. And let me mention a little more about the development. In the second half of the 20th century, actually, there is a branch called algebraic geometry. So algebraic geometry. Algebraic geometry. Okay. This branch of the mathematics is actually really beautiful mathematics. Okay. So what this branch of mathematics study is, we study solutions to certain equations. Study solutions to polynomial equations. Okay, to polynomials. Okay, polynomial equations. Okay, let's see fxyz equal to 0. Here fxyz is a polynomial in xyz. Okay, so it's a polynomial in xyz. You know, for plane and for line, the polynomial is degree 1. Okay, the equation is degree 1. That's easy. Now, there's no reason that we just restrict ourselves to low degree case. You may naturally ask, what happens in high degree? So this is actually a natural question to study. Study equations that has higher degree, not just degree 1. Okay. Now, of course, we can change the coefficient to R, to real. So when we study real solutions, real numbers, we may study integer solutions. Okay, integer solutions, which is called you know, arithmetic property. Okay, integer solution, or rational numbers. Okay, rational point. So this is actually a huge topic. Rational points, for instance, rational point on curves. Do we have rational solutions? Solve the equation by rational numbers or integer solutions. Okay, so we can find equations, solution to this equation from different point of view. Okay, from different point of view. This is, let me mention this, Grothendieck. This is also one of the greatest mathematician. He died in 2014. Okay, he's a member of Bourbaki. He was a member of Bourbaki. Bourbaki member. Bourbaki. Okay, Bourbaki school is actually a group of French mathematicians under certain age. Okay, probably under age 40. So they have a pseudonym. They call them Bourbaki. Okay. So Bourbaki is a mathematician that never exists. Okay, So they also wrote many books. Now, one of the style of this Bourbaki school is they actually working on 30 things that are really abstract. Okay, really abstract. This is the a current flavor of algebraic geometry, because algebraic geometry deal with a lot of things simultaneously. So to include a lot of things, so this makes the language really abstract and universal. So it can deal with many cases. Many cases will be just a trivial or just special cases of what in this system. Okay. Now it's really beautiful if you understand it, and it's really painful if you first learn it from abstract thing. So Grothendieck did is Grothendieck use a different language, use category theory. The idea is we understand object by relations of this object with other object, okay? Or more concretely, we see maps between objects. For instance, we talk about functions between different sets, okay, different sets. So Grothendieck used category theory to completely rewrite the language of algebraic geometry. So in some sense, Grothendieck is really influential of the 20th century mathematics. Okay. Many problems like a Fermat-Law theorem is actually solved using this kind of Grothendieck style language, Grothendieck tools. Today we cannot imagine without these tools how mathematics looks like. Okay, so Grothendieck rewrites algebraic geometry. So of course, Grothendieck is really good at abstract mathematical object. Okay, he just find the right abstract structure, no more, no less. Okay, to write mathematically. So it's really amazing in the 20th century. So he is really good at abstract things in the second half of the 20th century. Okay. You see this thing, this is solution to certain polynomial equations. Okay, certain polynomial equations. This is actually algebra with solving equations. This belong to algebra. Now, Grothendieck actually provide his language, provide a natural geometric thing. Okay, provide the right geometric intuition to understand the algebra. Okay, you see, we use geometry to study algebra in this case. Now, analytic geometry, we use algebra to study geometry. In some sense, the language that Grothendieck provide us today is exactly what happened, 300 years ago. Okay, what Fermat and Descartes did. Okay, and of course, Grothendieck, his language is actually another level of mathematics. Okay, so generalized analytic geometry in some sense. Okay, let's do some concrete case example. Let's see what this looks like. Example. Let's see example 1. Y is z squared. Y is z squared. Okay, y is z squared. Here x is free. X is free. So we can translate around x. We don't need to write about x, right? So when x is 0, so y equals z squared. So this is actually parabola. This is a parabola. So if this is the y-axis, this is z-axis. Now y equals z squared. This looks like this. So this looks like this. Y equals z squared. Okay, y equals z squared. Parabola. Now we actually, what we do is we translate the thing along the x direction. Okay, translate this along x direction. So suppose this is x axis. And then what we do is we translate the thing along x axis. Okay, so we get this thing translate. Okay, translate the thing along x direction. Okay, so let's plot these curves. Okay, so this will be, it looks like this. Okay, it will be a surface look like this. Okay, so we translate the thing. So this will be a surface look like this. Okay. Okay, so this will be the surface that we obtain. The surface that we obtain. So it's a surface in the three-dimensional space. Okay, so it translates the parabola along the x-axis direction, and then we get a surface. Okay, we get a surface. Okay, now what do we get for this plane, this surface? This is this example. Example. Xy equals 1. Here z is free. Z is free. Z is free means we can lift up and down, lift up or down of. So xy equals 1. So this is hyperbola. Okay, this is the hyperbola. So xy equals 1. So we get it. So we write in the xy plane. Okay, so this is the this is the x, this is the y. Now the hyperbola x times y equals 1, or y equals 1 over x. So what we get is, it looks like this. Okay, so we are plotting the thing on the xy plane. On the xy plane. Okay, it has horizontal and vertical asymptote. Okay, now z direction. Now we actually have z direction. Z is perpendicular to this. Okay, so we add a z direction. Z direction is this. Z direction. Now we actually, because here the variable z is free. Z is free, so that we can lift this the curve, the hyperbola on the xy plane. We can lift up or down. Okay, lift up or down. Okay, so actually we get actually a surface. So its surface look like this. Okay, the surface will look like this. It will be this surface. Okay, now this also curve. Of course, we have the surface. Surface. Okay, surface. Okay, and here we have this kind of surface. Okay. Okay, so this is what this looks like. This thing looks like. Okay. Okay, another equation. Another equation. Okay, this equation. Equation 3 is let's see, x squared plus y squared is z squared. this is okay. Suppose okay, let's see this. X squared plus y squared equals z squared. Okay, you see the height at starting particular z, this actually is a cone. This is the cone. Okay, so this is the cone. This is the cone. Okay, let me plot the cone and explain why this is a cone. Okay, why this is the cone. First of all, x squared plus y squared is x squared plus y squared is the distance of a point to the z-axis, okay, or distance squared. Distance squared. So this is z-axis. This is O. We have x, we have y, and we have z. We have z. Okay, z direction. Now, if you have a point, okay, if you have a point P x y z, okay, P x y z, you see the distance P to the z-axis is exactly x squared plus y squared. Okay, so x squared plus y squared gives us distance squared. Let d be the distance. Be the distance of P x y z to the z-axis. To the z-axis. Then we get x squared plus y squared is exactly d squared. So you see, we get d squared equals z squared. Okay, so this actually tells us d squared equals z squared. This actually tells us the radius is actually z. The radius is z. So if you cut at z, so you get a circle of a radius z. Okay, this circle of a radius z. And the intersection, suppose you cut it at x equals 0. So you cut x equals 0, you see we get y squared equals z squared. So it's a straight line. Okay, it's a straight line. So y is plus minus z. So you see, and then rotate this thing around. Rotate this line, y equals z, y equals plus minus z. You get, this is also called the generating line. Okay. Then actually you see the straight line, if you rotate along the z-axis, rotate around the z-axis with respect to the z-axis, then we get a cone. Okay, we get a cone. So this x squared plus y squared equal to z squared is the surface. Okay, is a cone. Is this cone? Okay, so it's surface of the thing. So it's this surface. This surface. Okay, this surface. Not including the it's not a solid volume. Okay, just the surface. Okay, so we get the equation of the cone. Okay, now let's just write down the general form of a quadratic surface. Okay, a quadratic surface, we can write it in this form. Quadratic surface. We just write down every terms. So the general form is ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus gx. We have a lot of letters, you see, hy plus iz plus j constant term is 0. Okay. Now actually we can write down a standard form. standard form, maybe fact. By using substitution technique, we can actually write in the standard form ax squared plus by squared plus cz squared plus z is 0. Okay, or we have this ax squared plus by squared plus iz is 0. Okay. Okay, I will not do this how explain how we actually the standard form. Instead, we will give several examples of surfaces in standard form and plot what it looks like. Okay. Let's see this example. Let's see this example. 1, z equals x squared plus y squared. This is obtained by, this is called elliptic paraboloid. This is the elliptic paraboloid. So this thing, you see, if we get a z squared, then we get a cone. Okay, then we get a cone. Now, this is also obtained by rotation, but actually we rotate it. You see, if we choose x to be 0, if we take x to be 0, take x to be 0, on the plane x to be 0, yz plane, then you get a z equals y squared. This is actually a parabola, okay, a parabola, okay. So this we get a parabola, okay. Z equals y squared. So it will be looks like a parabola. A parabola, okay. Z equals y squared. Now, if we have x, because here x squared and y squared is distance squared. You see, the distance is constant. So z is positive, okay. So you actually we rotate the thing. So we get this structure. So we get x, we get a y, we get an x. Make sure you have right-hand system using the right-hand rule, x, y, z. Okay, so this is actually the surface. Okay, surface. Okay, the surface. This is called elliptic paraboloid. In general form. The cross section, if you cut at a certain height z, what you get is a circle, or a circle is a special case of an ellipse. Okay, so we actually have elliptic paraboloid. So in this case, for instance, we may divide z by coefficient, and then x squared over a squared, y squared over b squared. Now for certain z, the right side, in the xy plane, for fixed z, if you cut at a certain height, what you get is actually an ellipse. Okay, an ellipse. So this is why we call it an elliptic paraboloid. And if you let x be 0, you see, you get y squared over b squared is z over c, which is a parabola. Okay, it's a parabola. Okay, so we call it the thing elliptic paraboloid. So for instance, x equals z, take x equals 0, so we get z over c is y squared over b squared, which is parabola. Okay, parabola. And we take z to be constant. Take z to be some quantity, some quantity. Let's see, z equal to capital T. We get a t over c. This is x squared plus a squared over y squared over b squared. Now, if you normalize it, so this gives us an ellipse. An ellipse. So this is called an elliptic paraboloid. And its picture looks like this form. Okay, its picture looks like this. But here, what we do is we put the circle into an ellipse. Okay, so will be an ellipse. Okay. Okay. Maybe this example. Ellipsoid. 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 Ellipsoid is this equation: x squared plus a squared over y squared over b squared plus z squared over c squared is 1. Okay, so this looks like a football. This looks like a football. You know, if a equal b equal to c, then we get x squared plus y squared plus z squared. This actually the unit ball. Sorry, the unit sphere. Unit sphere, just the surface. Okay, unit sphere. And then if you divide by a, divided by b, divided by c, in some sense, we actually rescue each x, y, z component. Then this actually, if we plot it, it will look like a football. Rescue the thing in 30 minor. Okay, so this. Okay, so if you have this is the x direction, and this is the y direction. Now this is z direction. Now this curve is essentially looks like a football with a rescue by rescue of a sphere by 13 factor. Okay, by 13 factor. The idea is exactly what we did for ellipse. Okay, we can rescue a circle. Okay, rescue a circle by 13 factor. Okay, then we get an ellipse. Okay, we get an ellipse. Now here when we do the thing for the ball, okay, for this sphere by rescue by 13 factor, we get ellipsoid. Okay, ellipsoid. So here a is here x coordinate of a is a, this y is b, z is c. Okay, z is c. Now if you cut x, y, z, you actually get a bunch of ellipse. Okay, ellipse. Whatever you cut at 30 thing, you actually get ellipse. You get a family of ellipse. Okay. Okay, we have 13 curves that yeah, actually next time we can plot. There are 13 curves that I have it here, but maybe next time we can plot 13 curves. Next time maybe we plot talk about it back to this topic again and see how we do it using computer package. Okay, and then we have and then now we start talk about next topic. Okay, we have 13 curves, 13 surfaces that we haven't done yet. Okay, next time we will plot this kind of surfaces. But now let's just continue another topic right now. Maybe one more curve. Let's talk about this curve maybe. Hyperbolic. This how to pronounce hyperboloid of 2 C's. Maybe this is easy to explain. Of 2 C's. This equation look like this. So it's negative x squared over a squared, negative y squared over b squared, plus z squared over c squared is 1. Okay. So this actually tells us that it's how do we plot it. So let's just plot a special case. So A, B, C, they are just 1. X squared negative y squared plus z squared is 1. Okay. So you see z, so you see z squared is, if you saw 1 plus x squared plus y squared, z squared is greater equal than 1. Okay. So it will be z is greater equal than 1 or z less than equal to negative 1. And then for certain z that in this range, then you cut at a certain z, you see you get this equation x squared plus y squared is z squared minus 1. So if you fix z, this is the circle, which is circle, a circle for fixed z, a circle for fixed z greater than 1, a circle. If z is 1, this reduced to a point 0, 0, 0, 0 plus minus 1. Okay, so then let's just plot it. Remember, z is greater than 1 or less than negative 1. So suppose it's 1 and this is negative 1. Okay, and then for fixed z in this range, so is the cross section, if we cut along z horizontally, then we get a circle. So this will be this, look like this thing. Okay, if we cut, we get a circle. We get a circle. Okay, we get a circle if we cut at a certain z. So this is this branch, and also of course we have another branch, another piece. It should be symmetric. It should be symmetric. Okay. So this is what this is called hyperboloid of two sides. Hyperboloid of CC of two sides. And we have hyperboloid of one side. Hyperboloid for instance, if what happens if you cut at 13x, if you cut at 13x, suppose you have any x, then what you get is actually this. For fixed x, this will looks like a hyperbola. Okay, hyperbola. If you cut, for instance, if you let x be 0, okay, if you let x be 0, then what the equation looks like is x, you take x to be 0, i.e. on the yz plane, this will be a negative y squared plus z squared is 1, okay? So this is actually the hyperbola, okay? Hyperbola. So the name is called hyperboloid, okay? So we, in some sense, rotate it, then we actually get hyperboloid, okay? Now let's see this. What did we get for this? Hyperboloid of one side. Of one side. Hyperboloid of one side. This equation looks like this. Okay, x squared over a squared in standard form. Okay, plus y squared over b squared minus z squared over c squared is 1. Okay. Okay, so let's maybe plot how this looks like. Okay, how this looks like. Okay, now you see, let's see this. We do some special case maybe. Let's see to be 1. So this is x squared. If you write in this form, x squared plus y squared over b squared is 1 plus, let's see z squared. So take c to be 1 without loss of generality. Take c to be 1. Okay. Now you see this always have the equation, have a solution. This always have solution for any z, okay? So actually it's for z it's actually continuous. Okay, there's no gap between z. Okay, now this is actually for fixed z, we get an ellipse. Okay, so it's a family of ellipse such that the ellipse becomes bigger and bigger if z becomes bigger and bigger. Okay, start from 0. So it will be looks like this. Now, if you take x to be 0, you get a hyperbola. Okay, if you take x to be 0, then you get so this is the ellipse, for fixed z, for fixed z. For fixed z, this gives an ellipse. Okay. Now, if we take x to be 0, for instance, x 0, then we get this y over b squared minus z over c squared is 1. So this is hyperbola. Then what we get is look like this. Somehow looks, if we cut the 30 section, it looks like hyperbola, 30 section looks like ellipse. Okay, ellipse. So we just plot its picture. So actually, you will see this very often somewhere. So the cross section on this is the ellipse. This is the ellipse, and here this is the ellipse. Of course, it's symmetric. It's symmetric. Okay, symmetric. When I just plot, it's not quite symmetric. Maybe here, x, y, and here we have z. Okay. Okay. All right. You actually this kind of shape is actually you can see this shape somewhere. For instance, the cooling tower in power plant. Cooling tower in power plant. Okay. Cooling tower. Actually, the surface of cooling tower looks like the hyperboloid of one sheet. Hyperbola of one sheet. We have another case, hyperboloid, hyperbolic, parabolic. So this case, we will actually talk about this next time. It's not easy to plot by hand. Hyperbolic, paraboloid. Its equation look at this. Z over c is x squared over a squared minus y squared over b squared. This we actually plot this next time. We will plot this surface next time. It's not very easy to plot. It requires a lot of work. And it's, of course, even if we plot it, it looks like a bit dark behind. So it's easier to compute, to plot by a package. Next time we actually continue plotting thing, use a package. Okay. Okay, now let's talk another topic, vector functions. Vector functions. Okay, actually, if you study engineering, one subject actually is necessary, like a vector analysis. So in some sense, it's calculus for vectors. Okay, calculus for vectors. Now, in calculus 1 and 2, what we often do is one-dimensional, integration. Okay, one variable, one-dimensional thing. Now, actually, we can do it for vectors. And then it turns out we have nice thing happens in higher dimensional. Okay, and the lower dimensional thing can be generalized to higher dimensional. Okay, and once we know the higher dimensional, this of course, if we know the higher dimensional thing, it helps us better appreciate what happens at the lower dimensional. Okay, So vector functions. This section is really easy. Really easy. Vector functions. Vector functions. We actually see this already when we solve vector form differential equations. So vector function is, you know, for instance, position function RT is xt, yt, zt. Xt, yt, zt. Okay, that's very easy. Here x, y, z, they are functions, real functions in variable t. Okay. Example. RT is let's see, x0 plus at, y0 plus bt, z0 plus ct. So we can write in vector form. Okay, so this will be x0, y0, z0 plus t times abc. So this actually the geometric picture is we have a point xyz, x0, y0, z0. Okay, p0, let's see. This is the x0, y0, z0. And then we translate this point along a vector v. Okay, let's see, v is abc. Okay, we translate it. So this is p0. This is the, and then we translate along the directional vector. So this is in the v direction. So we can have different position vector. This translation of the thing using directional vector. Okay, so this is actually a vector form of a line. Okay, so this is the vector equation, vector form equation of a line. Okay, more example. This example. RT is cosine t I sine tg tk. Okay, now if you forget about the z direction, so component wise, so x is cosine t, y is sine t, z is so z is t. Okay, so z is travel. Okay, the z position is uniform in t. Okay, so it's a constant velocity along the z direction. And then the xy, you see, xy is the parametric equation of the circle. So you see x squared plus y squared is cosine squared plus sine squared. So this is actually nothing else, just unit circle. So this is actually what we do is we extend the circle, okay, such that we travel a circle along the compose the motion of a motion that travel along the circle on, and then combine that thing with the z direction motion. So actually what we get is helix, okay, helix. So it looks like this. So xy without a z direction, it's just a circle, move along circle. But we have a z movement, so it will be this. So it will be, it looks like this. Okay. So it will be, this is the unit circle. Okay. This touches this ground. Okay. So this is the helix. Okay, just a remark. Now we actually have this kind of thing in nature. Okay, in nature. For instance, let me do a remark. the DNA model is, we have two linked helix. So two linked helices discovered by, we know the DNA model by Jans-Forsen and Crick. So we do have this thing. Francis Crick. So the DNA model. Okay. Okay. Next topic. Derivatives of vector functions. Derivatives of vector functions. Okay. Now, for vector functions, the derivative is just component-wise derivative. So dr over dt, we already have this dr over dt. This will be r prime division, and this will be using the definition h over 0 rt plus h minus rt over h. Okay. Okay. So this is the tangent vector. Let's see if we have a curve. Okay. So suppose the rt, suppose this is origin O, rt. So this is rt, and this is rt plus h. Okay, you see, if we subtract rt plus h, subtract rt, let me color that thing in red. Color that thing in red. You see, the difference is, okay, in red. So as h over 0, you see rt and rt plus h will looks like really close. Then actually we get the tangent vector. Okay, we get a tangent vector. So the derivative of the thing is actually the tangent vector, is in the tangent direction. Okay, so this is actually a tangent vector to the curve defined. So this is actually the derivative gives us dr over dt gives a tangent vector. Tangent vector to the curve defined by rt. To the curve defined by rt, r equals rt, at the point p. Suppose this point is p. Okay. And also the derivative is computed component-wise. Okay, component-wise. So if we have rt, so rt is xt, yt, zt. So rt derivative will be rt prime. This will be x prime, y prime, z prime. Okay. For example, if we know rt is cosine t sine t. This is actually the parametric equation of the helix. Okay. Now rt derivative gives us velocity. Velocity is you see cosine t, we get a negative sine t, sine t we get a cosine t, t we get a 1. Okay, so we get a velocity function. Okay, we have a very easy rule for derivative, like linear property and how derivative behaves with cross product and dot product. Okay, so differentiation rules. Differentiation rules. So we have this d dt, u plus v, ut plus vt is, this linear, this du over dt plus dv over dt, linear property. That's trivial, okay? Now derivative of linear property, c times u, cut. Let's use lambda maybe, which is a lambda du dt. Lambda is constant. Lambda is constant. And we have the product rule. Now if we multiply by a function, we multiply by a function f, multiply a vector by a scalar, but here the scalar is actually function scalar. So this we got f derivative, we have product rule. So this is actually just the product rule. You just write down the product rule component wise, okay? So you just write the component wise product rule. And we have the product rule for dot product and cross product. So for dot product, u dot v, then we get u prime dot v plus u dot v prime. Okay, so it's a product rule. Now cross product, we also have a rule for cross product. So cross product, we also have product rule. d dt, u cross v. This is a u prime cross v plus u cross v prime. Okay, then so this is the this rule, differentiation rules. Now we actually have this. If R is constant vector, constant norm vector, then example, if R is, its norm is constant, is a constant, then okay, R prime t, R derivative is orthogonal, orthogonal to RT. Okay. Now, how do we prove it? We use the chain rule. Okay. We use product rule. So, for instance, R dot R is a constant, norm constant, norm squared. So it's constant. Is a constant. Constant. Now differentiate both sides. Differentiate both sides. And then the right side derivative constant, we get a 0. Okay, derivative of the left side, we use product rule. Okay, and it's symmetric, so we actually get 2 copies of R derivative times R. Dot product. Okay, dot product. Now the right side we get a 0. Okay, this tells us that so R derivative dot product with R, this is 0. R derivative is perpendicular, is orthogonal. orthogonal to RT. Okay. Okay. So this actually tells us if a particle is traveling on a sphere. Okay, traveling on a sphere, then the velocity is always perpendicular to the position function. Okay, the velocity is always perpendicular to the velocity is always perpendicular to the position. Okay, so for instance, let's just take the two-dimensional case. Okay, let's do a circle. Okay, do a circle. So a circle. Here RT. Let's the unit circle. Let's do it for x is cosine t, y is sine t. Okay, so R norm is 1 unit vector. Okay, you see R derivative t. Cosine we get negative sine, sine we get a cosine derivative. Okay, so you see R derivative of t times RT. So we get negative sine t times cosine t plus cosine t times sine t. This is exactly 0. Okay, the two terms just cancel each other, so we get a 0. Okay. Of course, we can get the result for a sphere or for a ball, or you can get the thing. We can also get the thing for higher dimensional ball. Okay, for higher dimensional sphere, like you can have many variables x, y, z, t. Okay, x, y, z, w, or many variables, and you can of course define the equation of a unit sphere, okay, in any dimensional space. This conclusion is still true, okay? This conclusion is still true. Okay. Okay. We can also do integrals. We can also do integrals. Integral of a function. Okay, integral is also, when we talk about derivative is done component-wise. Also for integral, we can also define this as component-wise. Okay, so integrals. So suppose RT is actually continuous vector function. So so this RT, assume RT equals let's see, FGH is continuous. And actually we can just A to B RT derivative, RT integral. This is, we can write component wise. So it's the F, A to B F I component, A to B GT dt, and J, and then A to B H dt and K. Okay, component wise. Okay, component wise. Okay, we have 10 minutes. Let's talk about this topic. Our next goal is talk about curvature, arc length, and curvature. Actually, if you take calculus 2, you already know how to compute arc length. Okay, compute arc length. Arc length and curvature. Arc length and curvature. Curvature. Okay. Recall what we did in calculus 2. Okay, in calculus 2. So suppose you have a curve, a nice curve. Suppose you have a nice curve in the xy plane. This is y. Okay. So you have a nice curve, y equals fx, for instance. Now we use tangent line to approximate the curve, because tangent line is straight line. Okay, straight line, we have good matter about the length. Okay, so so this is we use, so this is dx, and then this is actually dy. Okay, so what is ds? ds is the arc length computed using tangent line. Okay, using tangent line, we use tangent line to approximate the curve. Okay, so ds is the arc length computed, not the true arc length. Okay, this is the length of this tangent line. Okay, tangent line segment. And then we have Pythagorean theorem. So ds squared, which we get dy squared, sorry, dx squared plus dy squared. Pythagorean theorem. Okay. Some fact: this ds computed using the tangent line. Okay. This actually gives us the main part of the arc length. The true delta s. Okay, delta x is the true value of curve length. Okay, curve length. They differ, so differs by ds by a higher order quantity, which vanishes if we take limit. So we can use ds, as the main part, of this, arc length. Okay, so the higher order just vanishes when we just take limit. Okay, so then we get this curve arc length. We get this will be a to b. We integrated arc length form. Okay, so this actually we integrate ds from x from a to b. Okay, so this we get this write down explicitly. So this will be ds. You take a square root, you get a ds, which will be square root dx squared plus dy squared. Now, if you factor out the dx, so this will be 1 plus dy over dx squared times dx. So the arc length form is obtained in this manner. Okay, so this will be a to b 1 plus dy over dx squared for this curve times dx. Okay. Now, if you have parametric form, okay, a plane curve with certain parametric relation, okay. So if you have a plane curve, so for a plane curve, with this parametrization, for instance, y equals ft, x equals gt, from let's see a to b. Then you see dx, the differential dx will be dx over dt times dt. This will be g prime t dt. Then dy will be dy over dt times dt. This is the f prime dt. So you see the differential, arc length differential, dx squared plus dy squared, which is ds, which is this square root. And this will be plug in dx dy. So it's g prime t dt squared plus ft derivative dt squared. And then if you factor out the dt squared, then what you get is gt squared plus f prime squared dt. Okay. Okay, if we are dealing with 3 components, then we get okay, if we have a space curve, for space curve, let's see, RT is given by FG, let's see, H, we assume the curve is nice in parameter t. Then we get ds is actually ds is this. ds squared is rt norm dt squared. Okay, this will be f derivative squared plus g derivative squared plus h derivative squared dt squared. Okay, so the length, arc length of a space curve will be we integrate arc length differential. So this will be f derivative squared, g derivative squared plus h derivative squared. Integrate the thing with respect to t. Okay, for instance, find this circular helix. Example. Find the length of this helix. Of the arc of the circular helix. Third circular helix. Okay, so its equation will be RT, which will be cosine Ti plus sine Tj plus Tk. Here T is from 0 to 2 pi. Then we find arc length differential. ds. This will be, now take a derivative component wise, okay? Component wise. So cosine T gives us negative sine T. Okay, we square it. Sine T gives us cosine T squared. Okay. And then T derivative gives us T derivative gives us 1 squared, okay? And then add this together. You see this is sine squared plus cosine squared is 1. So it's the, this gives us 1. So this actually ds is, don't forget dt. So ds is actually square root 2 dt. Square root 2 dt. So L will be 0 to 2 pi square root t dt. So this will be square root 2 t from fundamental theorem calculus. So we got this is 2 square root t pi. Okay. So this is the arc length of this helix for one circle. Okay. Next time we will talk about the curvature. Next time. Okay. Maybe it's a good time to stop here for today. Any questions?